who will talk to us about knowledge compilation and Boolean functional synthesis. So it's kind of a semi-follow-up maybe, or at least somewhat related to what we heard last week. So Supratik has done a lot of work on counting and sampling, formal methods, automata, logic, you name it. So, but we usually don't spend too much time dwelling on our speakers and their CVs. We just let them get down to it and give their amazing talks. So Supratik, without further ado, please.
Thanks, Jakob. Yeah, so last week, some of you may have attended a talk where I talked about some algorithms, which is particularly the guess, check, and repair paradigm for Boolean functional synthesis. So this talk is not going to go into that at all. So I'm going to talk about knowledge compilation. But of course, there is a bit of overlap in terms of the introduction and the related work and so on. So my apologies for that little bit of overlap. But hopefully we will soon go beyond that and talk about knowledge compilation. Okay, so this is joint work with my colleagues Akshay, Krishna, and Shetal, and students Jatin, Ajit, and Divya. And let's get to some motivation right away. And Boolean functions are often easy to specify relationally rather than as directly as a function in terms of the inputs. So here is a simple example, and I also want to talk about another example in today's talk. So this example talks about an arbiter where there are two Boolean valued requests and two Boolean valued grants. And let's say this is a very simplified arbiter. So we are talking about the grants just depending on the requests at that particular point of time, at the same instant of time. So one could think of specifying the behavior of this arbiter by saying that if there is an input, then if there's an input request, then at least one of the output requests should go high. The arbiter shouldn't be denying to both the requesters if at least one of them has requested. And of course, this arbitration is happening for a shared resource, so both of them should not be granted at the same time. And if grant 1 has been set high, then there must have been a request on requester 1 must have requested something. And if grant 2 has been set high, then requester 2 must have requested something. And of course, one could develop this further. And in fact, one could even talk about an arbiter where the properties are stated with respect to some temporal specifications. But just to keep things simple for this motivating example, we're just talking about a combinational view of the arbiter. Okay, so if you look at the specification, we don't know what G1 and G2 are as functions of R1 and R2. But if we have to design the arbiter, we need to obtain G1 and G2 as functions of R1 and R2. And in this particular case, there are more than one solutions. For example, 2 of the solutions are shown here. Any one of these, if you pick, if you choose G1 to be R1 and negation R2 and G2 to be R2 and the other solution being symmetric, if you choose any one of these solutions, then if you plug it in, you will see that it satisfies the specification. So the question is that starting from the given relation between inputs and outputs, how do I obtain the outputs as functions of the inputs? And this is the Boolean functional synthesis problem. We are trying to synthesize Boolean functions from a relational specification. The specification is propositional. It doesn't have any temporal operators in it, and therefore the functions that we are trying to synthesize are also going to be propositional functions or combinational circuits, which when plugged into the specification should satisfy the specification. Okay, so the formal definition is as follows. So we are given a Boolean relation, which is the formula phi. The input variables are denoted in blue. That's the notation I will be following throughout. The output variables are in red, and a vector of input variables and a vector of output variables are represented by these capital X and capital Y. And what we want to do is, given this specification phi in terms of the inputs and the outputs, we want to synthesize functions f1 to fm, one for each of the outputs, such that for every value of x, if there is some way to satisfy the specification, which means that there exists some values of y1 through ym, which will cause phi to evaluate to true for that value of x, then f1x till fmx will also satisfy the specification when plugged in place of y1 through ym. Okay, so what this is saying is that I can effectively obtain witnesses for these existentially quantified variables by using these functions over here. And whenever there exists a value for these existentially quantified variables that makes the formula, that makes the specification true, then the functions also serve that purpose. And in the literature, these functions fjx are also called Skolem functions for the output variables in terms of the inputs. So we're going to use the same notation in this talk as well. Now, there are a couple of things to note here. The first is that if the number of inputs is small, then this is not a very interesting problem, because I could just enumerate all the 2 raised to cardinality of x valuations of the inputs, and for each one of them I could make a sat call, find out the values of y, and just tabulate them. So this problem is interesting when the number of inputs is large. Interestingly, this problem also stays interesting when the specification is quote unquote unrealizable, as in the classical definition of realizability. So in the classical definition of realizability, we say that a specification phi is realizable if for every value of the inputs I can find some value for the outputs, which makes the specification true. But what we will see very shortly is that there are indeed several cases, several interesting specifications where it is not the case that for every value of the input I can find an output that makes the specification true, but there are indeed interesting cases of the inputs x for which there exists y, and it is for those x's that I do really care about finding the right values of y. So even if the specification is unrealizable in the classical sense, this problem is interesting as long as there are some x's for which I can find y's such that the specification is true, and for those x's my Skolem function should give the right values for y, and for the other x's for which there are no y's such that the specification can be made true, the value of the Skolem functions are completely inconsequential. Okay.
So quick question.
Yeah.
Yeah. Go ahead. There are unrealizable specification. Can you give an example?
Oh yeah, I'm just coming to the next slide. Yeah, it's there in the next slide. So here is a very interesting example of an unrealizable specification, which relates to bounded integer factorization. So suppose I have 2 n-bit integers, call them y1 and y2, and I have a 2 n-bit integer, call it x. And my relational specification says that x is the product, the n-bit unsigned product of y1 and y2, and y1 is not equal to the n-bit unsigned integer 1, and y2 is not equal to the n-bit unsigned integer 1. So if you view this as a formula, this is just relating x, y1, and y2. And of course, if y1 and y2 were inputs and x was an output, there would be an easy way to synthesize this. Just, let's build a multiplier circuit. But the interesting case happens when we treat x as an input and y1 and y2 as an output, because in that case, we are really asking for non-trivial factors of x, of the integer represented by x. And this is an example of a unrealizable specification in the classical sense, because if you feed a value of x which denotes a prime number, then there are no values for y1 and y2 which are going to satisfy the specification, because the only factors of a prime number are itself and 1, and we have disallowed either of the factors from being 1, right? So this specification can be satisfied if you treat x as an input and y1 and y2 as outputs. This specification can be satisfied only for non-prime x. For x which represents a prime number, there are no y1 and y2 which satisfies this. And of course, I don't need to emphasize to this audience that this is a very important problem. This is the factorization problem. In fact, the hardness of cryptographic protocols that we have, a lot of them depend on the hardness of not being able to factorize the product of two primes, right? So if I give such a product, there are just two primes that will serve as the values for y1 and y2. But if I could solve this problem efficiently, then I would be able to crack those crypto systems. So this is a hard problem. So it also tells us that it's not going to be easy to solve this problem. And we are really asking for every non-prime x, find non-trivial factors. And for prime x, of course, we don't care. Now, there is, since this question came up about, what are other unrealizable specifications? So there is yet another, very, very important class of unrealizable specifications that we deal with is when we are doing, let us say, temporal synthesis, and we, construct a winning region, and we try to ensure that whenever we are in a state, we take a transition into the winning region. Now, it could indeed be the case that from certain states, there are no transitions to the winning regions. So once again, the specification is unrealizable in that sense. But indeed, we want to make sure that a controller that we synthesize is such that from every state, if there is a way to come into the winning region, we do apply those inputs that get us into the winning region. So actually there are, board games are another example where from every position you may not have a winning move, but you do want to come up with a function such that for all positions from which you have a winning move, you do want to take the winning move. So there are actually a lot of classically unrealizable specifications, but for which it still makes a lot of sense to find out these column functions. Okay. So did that answer your question?
Yes.
Okay, thank you. Okay, so, and there are, as I said, lots of applications of this problem. So cryptanalysis, it is interesting, but this we know is going to be hard. There is an application where you're given a symbolic state transition relation, and you want to disjunctively decompose it, which means that the union of the transitions in the various components are the set of transitions in the original state transition diagram. And so this disjunctive decomposition can also be reduced to Boolean functional synthesis. And of course, quantifier elimination. This comes from the definition of Boolean functional synthesis, that we want to get f such that when I plug in f for y, I achieve the result of quantifying out y from phi. Certifying QBF SAT solvers, as I said, we are really getting a witness, a certificate for y when we are saying that this function evaluates to true, this specification evaluates to true. And there's a nice survey of applications of certificates of QBF SAT solvers that was published in a recent paper. Reactive controller synthesis, I already described this briefly. We want to synthesize moves to stay within the winning region. This program synthesis also, combinatorial sketching and complete functional synthesis, both of which can be thought of, can be reduced to, finding column functions that satisfy a specification like this. And of course, in program synthesis and complete functional synthesis, one may be interested in going beyond Booleans. For bit vectors, we can still sort of blast them and reason about them in Booleans, but this problem is interesting even when you're talking about integers or reals or rationals. Then there are also applications in repair and partial synthesis of circuits, where once again it amounts to solving this quantified formula by finding a certificate of the existentially quantified variables. So there are a bunch of applications, and this is some sampling of those. And of course, since there are applications, people have also tried to solve this problem, and there's a very rich literature on solving this problem. Interestingly, more than a century back, George Boole and close to the beginning of the last century, Lowenham looked at a problem which is called finding the most general unifiers for propositional formulas. And there's a close connection between finding most general unifiers and Boolean functional synthesis. Much later, the algorithms that Boole and Lowenham, the methods that they had proposed for finding most general unifiers, which can be used to find Skolem functions, were also tried out, implemented, but unfortunately they turn out to be very inefficient in practice. Interestingly, Skolem came much later than, the Skolem functions were introduced in the 1920s, but much before that, people were already studying problems which had close connections with Skolem function synthesis. There's also this very nice, sequence of papers which talks about that, well, if the formula, if I'm indeed talking about realizable specifications, then the formula for all x exists y phi of xy is valid, and therefore there should be a proof of validity of this, and it should be possible to extract from that proof of validity the witness y for every value of x. And indeed this has been used quite successfully. Interestingly, this can be used only for realizable specifications, which is of course a very important class of specifications. But when we want to talk about things like integer factorization, the specification is not realizable, so this formula is not valid, so we can't use this technique. There has been work where templates have been used, templates for the Skolem functions, and then you can suitably instantiate the templates and sort of check whether they're satisfying the formula. There's a very classical line of work which involves self-substitution and function composition, and I'm going to talk about these a little bit as we go deeper in the talk. But the primary focus of today's talk is going to be synthesis from special normal form representations of the specification, and I'm going to talk briefly about work done by several other groups about synthesizing Skolem functions from RbDDD's representations of the specification, and then I'll talk about how we have been able to generalize that to something called a synthesis negation normal form. So this will be the primary focus of today's talk. But of course, yeah.
Is it important at this point that we can parse RbDDD or SynNNF, or you'll take, should we feel intimidated, or you'll tell us later?
I will be talking about both RbDDDs and SynNNF later. I just wanted to highlight this as one of the existing approaches.
Okay, great, thanks.
So I will be talking about these later in much more detail. Then there is a very interesting line of work, by Marcus Rabe and Sanjit Seshia, where they basically take the essence of how CDCL solving works, and they convert it to a technique which they call incremental determinization, which can be used to find out Skolem functions from a specification given as a CNF formula. There have also been quantifier instantiation techniques in SMT solvers recently, particularly in the Cygus competition. These kinds of solvers have been very successful, and those can also be used to solve Boolean functional synthesis. We have done some work earlier on what is called input-output component separation. I'm not going to be talking about this further, And in the talk last week, I really had elaborated a little bit more on the guess, check, repair paradigm, which also has turned out to be a very successful paradigm for solving this problem. But today's talk will be primarily focused around synthesis from special normal form representations of this specification. Okay. So we are going to ask that, what kind of representations of the specification can perhaps make the Skolem function problem easy. And in order to do this, we have to sort of decide on how are we going to represent the specifications so that we can then talk about special forms of those representations. So throughout this talk, I'm going to be using Boolean circuits, which are basically directed acyclic graphs with conjunction, disjunction, and negation labeled internal nodes and variable labeled leaves to represent both the specification and the Skolem function. So our specification is going to be a circuit which has the inputs xi's and the outputs yj's, and the output of the circuit is the propositional formula phi of xy, which represents the specification. Now, why do we choose these general Boolean circuits to represent specifications? Because if you give me other forms of specifications, let us say binary decision diagrams or conjunctive normal form formulas or disjunctive normal form formulas, or other forms in which you want to give the specification, it can be very easily converted to these Boolean circuits. And so we sort of took this Boolean circuit as a general enough form for representing the specification. And what I want to do is, at the end of Boolean functional synthesis, I also want to get another Boolean circuit, but this time this circuit is going to have only the x's as inputs, and it is going to have one Skolem function for each output variable y. Okay, so this is also going to be a circuit, and this will be a multi-output circuit. So each of these functions fi's will depend only on the x's. And as you can see in this figure, it is perfectly possible that subcircuits can be shared. For example, the output of this OR node here feeds into this AND node, which finally drives this f1x, and the output of this OR node also drives fkx. So it's perfectly possible for subcircuits to be shared over here. This is a general Boolean circuit that we're talking about, multi-input, multi-output. So the important point is that we are not saying that we want the Skolem functions as an RbDDD, which would be a special, which would translate to some special kind of circuits, or we are not saying that we want the output to be a CNF or a DNF. We are just saying, can we get just a Boolean circuit as the output? Now, once I say that, I'm going to sort of do my reasoning by assuming the input specification is given as a circuit and the output specification is given as a circuit, is the output Skolem functions are obtained as circuits. You will agree that any complexity theoretic lower bounds that I can obtain for this problem, where the inputs are given as circuits and the outputs are obtained as general circuits, any complexity theoretic lower bounds will also apply when I put more restrictions on, like, I want the outputs as RbDDDs, or I want the inputs to be represented as CNF, and so on, right? Because any lower bounds that I obtain going from a circuit representation of the specification to a circuit representation of the Skolem function, as long as those lower bounds are more than polynomial, will also apply if, let us say, I want to go from RbDDD specifications to RbDDD Skolem functions, or CNF specifications to RbDDD Skolem functions, and so on, right? Because there are easy translations from each of these forms to to the input specification as a circuit, and a lower bound that I get for a general circuit must also hold for a very special form of a circuit if I want that. So this representation kind of serves as a nice starting point for asking how hard is this problem going to be in general. What are the lower bounds? And it is not surprising that this problem is NP hard. This is fairly easy to see. You can take a SAT problem and just existentially quantify out all the variables and say that, well, these are all my outputs. I have no inputs. So the outputs now have to be generated as constants by your Skolem functions. And of course, this will solve the CNF SAT problem. So it's, of course, NP hard. The interesting question that we want to ask is that, okay, now that we know it is NP hard, so we are not going to get a very time efficient algorithm. But even if I was willing to spend exponential time, is it possible to synthesize compact Skolem functions, right? So can I ensure, okay, I think there's an echo from somewhere. So can I ensure that I'm going to get small Skolem functions at the outputs, and I'm willing to spend as much time as is needed for that? So we basically asked that, can we always do this? Can we always generate compact Skolem functions? And typically, when we are talking about these lower bound results for circuit size, typically we refer to monotone circuits, and there are, of course, these seminal results from Rasborov and Alon and Bopanna. However, this talking about monotone circuits is probably not the right thing in our context, because a monotone circuit has this property that if you change an input from 0 to 1, the output cannot change from 1 to 0. And there's no reason to believe that Skolem function should be monotone, right? So if Skolem functions are not monotone, then I can't really apply these circuit lower bounds for monotone circuits. And one might therefore ask that, well, since these circuit lower bounds for monotone circuits are not going to apply, is it possible? I mean, since we have this full generality of, we can put and or not gates wherever we want in our Skolem functions, is there reason for hope? Can we always get small Skolem functions as circuits? Unfortunately, a couple of years back, we were able to show that unless the polynomial hierarchy collapses to the second level, there exist specifications for which the Skolem function sizes must be superpolynomial in the size of the specification. And a slight extension of that argument shows that unless the non-uniform exponential time hypothesis fails, of course, this is this is a very strong hypothesis, the non-uniform exponential time hypothesis. But unless that fails, it's still open whether it is it stands or it fails. But unless it fails, then there exist specifications for which Skolem function sizes must be exponential in the size of the specification. And the basic argument behind these is not very hard. It's really saying that you can use the Skolem functions to sort of do lots of interesting things once you formulate the problem appropriately. So, well, given this bad news, we know that Skolem function synthesis, Boolean Skolem function synthesis, is not going to be time efficient or space efficient in general, and so we cannot hope for efficient algorithms that will work in general. Okay, but of course, that doesn't mean we should, give up solving this problem. This is an important problem, and we basically investigated this problem a little bit further, and we found out that if we could represent the specification in some special normal form, then indeed we can show that the Boolean functional synthesis problem can be solved in polynomial time and space. And this was interesting, and this basically led us to the main subject of today's talk, which is the synthesis negation normal form. And as I'll show you, that this subsumes well-known forms like reduced ordered binary decision diagrams, even functional decision diagrams, decomposable negation normal forms. Adnan talked about it in a very beautiful talk in a couple of weeks back, or maybe it was last week. And we will show that the SYN NNF subsumes these things. Of course, there is a caveat here that given the conditional lower bounds we have, this does mean that compiling a given specification to SYN NNF cannot be efficient in general, because once it is in SYN NNF, after that synthesis is polynomial time and space, and we have some lower bounds saying that synthesis is not going to be easy. It's probably going to be super polynomial time and space. So this means that there will be hurdles in general in compiling a given specification to an arbitrary specification to the synthesis negation normal form. But the silver lining is that our experimental evidence seems to show that SynNNF and something called refined SynNNF, which I will be talking about more detail, is actually not very uncommon in practice. I mean, we've found a large percentage of our benchmarks that we have been looking at to have these refined SynNNF form, or to be easily reducible to a refined SynNNF form. In addition, because as I mentioned here, and as I will explain later, that SynNNF, since it subsumes reduced ordered binary decision diagrams and decomposable negation normal form, so if I could compile my specification to reduced ordered binary decision diagram using any variable order to a functional decision diagram or a decomposable negation normal form, I already have a SynNNF, and after that, synthesis is easy. And of course, RbDDDs, DNNFs, these have been studied for a long time, and there are very mature compilation tools that exist. So we could also use these to sort of get to SynNNF, and from there do efficient synthesis. Okay. But as I said, because SynNNF subsumes all of these, we actually don't require the full capabilities of the strong normal forms, and I'm going to discuss this in more detail. However, we can use existing tools that are used for such compilation to compile to SynNNF, to sort of restricted forms of SynNNF. Okay, so let's see, what lies at the core of this Boolean functional synthesis problem. And to begin with, I will start off by saying that suppose I have just one output. So the cardinality of the vector of outputs y is 1. And I now have to find a single function, fx, such that for every x, whenever there exists a Boolean value for this single output variable, which satisfies the specification phi, if I used f of x in place of y, the specification will also be satisfied. So this is the single output case. And we can actually understand what's going on in the single output case very clearly. So this part is, this slide and the next are what I had also shown in the talk last week as part of the TFCS seminar. But I think let's go through it so that it sets the tone for what's coming next. So here I have represented the set of all valuations of x. Remember that x is a finite vector of Boolean variables. So of course, I can conceptually think of the set of all possible valuations of x. There are only finitely many of them. And then suppose I ask that what is the subset of these valuations of x for which I cannot set y to 1 if I were to satisfy phi, right? So I'm asking, which are those x's such that, if x takes on those values, then it would not make sense to set y to 1 if we were to satisfy the specification. And this is obtained very simply by taking the specification phi of xy, setting y to 1, and then just negating it, right? So this gives you all the valuations of x such that, if x took one of those values, and if you set y to 1, then of course phi will evaluate to false, right? So here's a simple example. Suppose phi was this CNF formula, and I want to find out what are the values of x, x1 and x2, for which it doesn't make sense to set y to 1. So all I'm going to do is I'm going to set y to 1 in this formula. So I'm going to get x1 or 1 here, x1 or x2 or 0 here, and then I'm going to negate the conjunction of these two clauses, and that gives me negation x1 and negation x2. And you can indeed see that if both x1 and x2 are false, then this specification phi simplifies to y and negation y, and there is, it doesn't make sense to set y to 1. In that case, if both x1 and x2 are set to false, you cannot make the specification true in that case. Okay. Now I could ask a similar question, that what are the values of x's for which it doesn't make sense to set y to 0? And the answer is very similar. So just take phi of xy, set y to 0, and negate the function that you get. And similarly for this example, I set y to 0 here and negation y to 1 here. And then when I simplify it, I get negation x1. And once again, if you see that if you set x1 to false, then this specification simplifies to y conjunction something. And since it is y conjunction something, it doesn't make sense to set y to 0 if you want to satisfy the specification for those values of x. Okay, so this is all good and simple. And we could superimpose these two sets, which I call gamma x and delta x. Gamma x are those values where you can't set y to 1. Delta x are those values where you can't set y to 0. And indeed, there could be some overlap. It just means that when x takes on any of these yellow values, then there's no way to make the specification true. Regardless of whether you set y to true or false, the specification will evaluate to false. And these white or non-colored circles, these represent the cases where you can set x to true or x to false, and the specification will be satisfied in both cases, right? So in this yellow cases, you can set y to whatever, and the specification won't be satisfied. In the white cases, you can set y to whatever, and the specification will be satisfied. In these red cases, you must set y to 0. It doesn't make sense to set y to 1. And in these green cases, you must set y to 1. It doesn't make sense to set y to 0. Okay, and it's not very hard to show from here that every Skolem function for this single output y must be an interpolant between this green region and the red region. Okay, so if I call that delta minus gamma and gamma minus delta, so it must be an interpolant between delta minus gamma and gamma minus delta, which means that it must evaluate to true in this green part, and it must not evaluate to true in this red part. At every other place, it's fine. You can include as many of the yellow dots or white dots, it doesn't make any difference. And this is nice because we are able to sort of synthesize y very nicely. And we can look at specific interpolants, which are actually very easy to compute. So for example, this part shaded here is just saying negation of the part where you should not set it to 1. Right? So gamma was the part where you shouldn't set y to 1. So you take the negation of this whole thing, that's already an interpolant. Or you can take delta where you shouldn't set it to 0, and therefore you set it to 1. And this is also going to be an interpolant. And it's not hard to see that both of these are actually interpolants between delta minus gamma and gamma minus delta. So these two interpolants are just obtained by taking the original specification, plugging in 1 for the output variable, and using that as the Skolem function. And this is take the specification, plug in 0 for the output variable, negate the specification that you get after that, and that will serve as the Skolem function. So we are going to primarily focus on this specific case, which is just obtained by setting 1 to the output variable if there is a single output variable. But one could also do whatever reasoning we are saying by taking negation phi of x0, that's also fine. So just for convenience, I'm going to go ahead with phi of x1. Okay, so this was fine. But now, if there was just one output, perhaps it was not a very interesting problem. So what happens if I have multiple outputs? Okay, and so here is a simple example where I have two outputs, y1 and y2, and two inputs, x1 and x2. And the first thing that you note is that because I have y1 XOR y2 as a conjuncted, as a clause that is conjuncted here, therefore whatever Skolem functions I get for y1 and y2, if they have to make the specification phi true, they must be the logical negations of each other. And this is kind of our first stumbling block, where we realize that when we have more than one output, we cannot synthesize these outputs independently. They are intertwined in general. Okay, so this is bad news because we had found a very nice way of solving the case for one output. So we asked that, well, can we do something to reduce this to a synthesis problem on one output? And the answer is yes, kind of yes. And what we want to do is we want to say that informally, we want to say that, okay, let us synthesize f2x such that if I use that f2x, I can always find some value of y1 later on, which will satisfy the specification, right? So remember, there are these two outputs, y1 and y2, and I realize that, I can't synthesize them independently. So I'm saying that, okay, let's just ignore the output y1 for the time being, and let's synthesize f2x. But while synthesizing it, we should somehow ensure that whatever function I synthesize, if I plug that in for y2, I can later on find a value for y1. For each x, I can find a value for y1 such that this formula is true. So informally, we want to do this. And if I were to formalize this, I'm basically saying that let's look at this formula, exists y1, phi of x, y1, y2 as the new spec. So I call this phi1 of x, y2, right? So this is kind of like a dirty trick that we are doing by saying that, well, we don't know how to deal with multiple outputs in a nice way. So let's pretend that we just want to deal with one output, and let's make sure that the specification from which I'm going to synthesize this one output is not the original specification, but it is derived from the original specification in such a way that if I plug in whatever f2 I synthesize for y2, then I can subsequently find a y1 which I can plug in for y1 in the original specification and make the specification true. Okay, so this sounds like a hack, one way to proceed forward. Let's see what happens in our case. So in our case, which is this example, x1 or x2 or y1 conjuncted with y1 XOR y2, if you existentially quantify out y1 from here, you get this formula, x1 or x2 or negation y2. And now this is a specification with a single output, and I can now go ahead and just set that output to 1, and I get this as my scolem function for y2. And because I had synthesized the scolem function not from the original specification, but from this new specification, which was derived from the original specification by existentially quantifying out y1, therefore I know that whenever I plug in this f2, I will have a way of getting y1 in terms of x. And so that's exactly what we're going to do. Once we have f2, we're going to plug in f2 over here, and that will give us a specification which just has y1 and x in it. So once again, it's a single output specification, and I can again do the same trick. So in this particular case, by plugging in f2x is x1 or x2 in the specification, I get this as my new modified specification, x1 or x2 XOR y1, and then I can just plug in 1 for the only lone output variable that's present here, and that gives me negation x1 or x2. And let's just cross check whether this all of this made sense. So I'm saying that if y1 is negation x1 or x2 and y2 is x1 or x2, then of course they're negations of each other. And so this y1 XOR y2 clause will evaluate to true. And here you see x1 or x2 or y1, and y1 was negation x1 or x2. So therefore this also evaluates to true. And this works for all x's, for all values of x1 and x2. So this worked for this little example over here. Now, if we were to generalize this, and if we were to go beyond two outputs, what would we need to do? Okay, so what we'll do is we'll first fix a linear ordering of the outputs, and it will become clear very soon why we are talking about linear ordering. So you can choose any linear ordering, but let's take a linear ordering. Let's say it is y1 through ym. And what I'm going to do then is I'm going to say that, well, okay, I'm just going to extend this idea of coming up with a new specification by quantifying out some of the output variables. I'm just going to, repeat this for all of these variables in a particular order. So for example, the first time I will quantify out all variables from 1 to m-1. So these are the variables shown boxed over here. And once I do that, I'll get a specification just in terms of x and ym. And that's a single output specification. I know how to get a scolem function out of it. Okay. Then the next time around, once I get that scolem function for fm, I'm going to substitute that here. So I have shown by these double squares over here the substitution that's happening. And then I'm going to quantify out all the variables from y1 to ym-2 in this new specification. And if I do that, you will see that these variables will be gone. Ym is already expressed in terms of x. So now again, you're going to get a specification only in terms of x and a single output ym minus 1. And we know how to solve that problem. I'm going to synthesize fm minus 1x from this adapted specification. And I could continue doing this until I finally reach the first variable y1, at which point I have already obtained Skolem functions for all the other variables. So I'm going to just substitute all of them. There is no further quantification needed. And once again, this is a one output problem, so I know how to solve it. Okay, so this could be a way of sort of dealing with arbitrarily many outputs. And the ordering here is clearly, you can see that we have basically generated the Skolem functions as per this order. You can take any order and we can do this. But now the big question is that it appears from this strategy that this quantifying out a bunch of these output variables and composing these Skolem functions that I have obtained from some of the steps that have already been taken, these two things appear to be very central in this scheme. And the question is, can I do this efficiently? Okay, so if I'm given the specification phi involving multiple outputs, I can indeed follow this strategy over here to synthesize all the Skolem functions, but I can do it only if I can sort of do this quantifying a bunch of variables and substituting Skolem functions for the other variables. If this operation, if I can do efficiently, then we are in business. And this turns out to be the central question that we need to answer, that is there a normal form, is there a representation of the input specification that will allow us to do this efficiently? Okay, so what I'm going to do now is, as promised, I will talk about RbDDDs, and in fact, it turns out that RbDDDs with some kind of variable ordering enjoy this nice property that you can do this thing efficiently. And I'm just going to illustrate that, how it works. So, there's, of course, there's a whole bunch of researchers who have tried to use this technique and develop for several optimizations on top of that. So here what we're trying to do is we're taking the specifications in RbDDD, and this we want to generate the Skolem functions also as RbDDDs, not just arbitrary Boolean circuits. All of these work also generate the Skolem functions as RbDDDs. And let me just show what an RbDDD is. I'm sure most of you here are familiar with it, but just for the sake of completeness. So it is a directed acyclic graph in which the nodes are labeled by variables, Boolean variables, and each node has exactly two children. One is connected through a dotted edge, and the other is connected through a solid edge. So the dotted edge represents the low child or the zero child. The dotted edge, the solid edge represents the high child or the one child. And this, you can think of it as a big decision tree folded into a DAG. So here we are saying that if x1 is false and x2 is true and y2 is false and y1 is true, then the function evaluates to 1. But if x1 is false and x2 is false and y2 is false, then regardless of the value of y1, the function evaluates to 0, and similarly for the other paths. And there is a very rich literature, very, very beautiful, elegant work which talk about how to represent Boolean functions using RbDDDs and the nice properties that you have when you represent Boolean functions as RbDDDs, different kinds of compositional properties you have. So the key point for our purpose is that, for our discussion, is that suppose I represented this specification as an RbDDD like this, then can I do synthesis from this efficiently? In particular, can I do that quantification and composition efficiently? And it turns out that it can be done efficiently if the variables, I must also say that in an RbDDD, it's reduced ordered binary decision diagrams. There is one key property that if you take any path from the root down to a leaf, there are only two leaves, 0 and 1. if you take any path from the root down to a leaf, the order in which you encounter the variables are going to be the same. So for example, here if I take this path, the order in which I encounter is x1 before x2 before y2. If I take this path, I once again get x1 before x2 before y2, and here also y2 comes before y1. So any path that you take, the order in which you encounter the variables are going to be the same. And it is known that depending on which ordering you use to construct your BDD, to represent the same Boolean function, you may get a very large BDD or a small and compact BDD, and therefore finding the right variable order to represent your Boolean function or specification as a BDD is, of course, an important area of study. And what researchers have shown is that if you order the variables, remember the function that we want to represent is a specification which has some inputs and some outputs. And if you order the variables while constructing the BDDs such that the inputs come first. So for example, here you can see the blue x1, x2 come before the red y1, y2 in all paths. So this is called the input first ordering of variables. So if you construct your RbDDD, reduced ordered binary decision diagram, using input first ordering of variables, the inputs could be ordered within themselves in whatever way. Every permutation of the inputs is fine, every permutation of the outputs is fine, but all the inputs must show up before any of the outputs in any path from the root to a leaf. And if you do this, then you can do the easy quantification of yi's and the composition of fjx's that we talked about in the earlier slide. And let me just illustrate this. I mean, the basic intuition behind this is actually quite straightforward. If your input variables are coming first, then after you have traversed the input variable, so let us say I'm saying x1 is false and x2 is false, and I'm at this node, right? Now, if from this node, there is a path to the one leaf, it means that there is indeed a way to assign values to y1 and y2 such that you'll reach this one leaf, which means the specification will evaluate to true. Similarly, let us say if I come, x1 is true and x2 is false, and I reach this node, and if once again from this node there is a path to the one node, it means that there is indeed a way to assign a value to y2 and y1 such that you'll reach the one node. In fact, there could be multiple ways of reaching the one node. There could be multiple valuations of y1 and y2 that you can use. And you can clearly see here, so for example, suppose x1 is true and x2 is false, and now I need to choose the values for y1 and y2. You can clearly see here that the values of y1 and y2 are correlated. If y2 is false, then y1 has to be true. If y2 is true, then y1 has to be false, right? If y2 is false and y1 is also false, then you will not end up satisfying the specification because you'll end up at the zero leaf. So really, if you order the input variables first, then after you have traversed the input variables, you could be standing at each of these nodes, the nodes labeled y2 here, and you could just read off the values for y1 and y2 over here, right? So for example, here I could say that, well, I should set y2 to true, because if I do set y2 to false, I'll reach 0. And after I have set y2 to true, then from here I should set y1 to true, because if I set y1 to false after that, I'll reach 0. And so therefore, at this point, after traversing the inputs, you can actually find out what should be the value for y1 and y2, and similarly at all of these points. And this now allows you to construct an RbDDD for y1 and y2, because right at this point you can figure out whether y2 should be true, and if y2 should be true, then what should y1 be, and so on. In terms of the notation that we had used earlier, at this point, if I say that, okay, does there exist a y1 such that phi xy evaluates to true? All I'm asking is that from here, is there a path to go to 1? Okay, because the values for x are already frozen by the path I have taken from the root to come here. And now I'm asking, does there exist a value for y1 which will let this specification be true? So it's really asking that, well, from here, does there exist a path to the one leaf? And if I were to take the path to the one leaf, what should be the value for y2? So that's what I get here, right? So there exists y1, phi xy is y2 here. So at this point, if x1 is 0 and x2 is 0, only if you set y2 to true, there will exist a value for y1, which will cause the specification to evaluate to true. And once you have this, you can just set, this is like a one output specification. So you can set that output to 1 to get the scaling function. So you get y2 as true. And once you have y2 as true, you know that you have basically followed this branch in RbDDD. So now you come here and you say, okay, now I want to find out what is the scaling function for y1. And you just substitute 1 over here. So you come here and then you see that y1 also has to evaluate to true, and that's what you get. Okay, so this is the basic idea of input first ordered RbDDDs and synthesis using input first ordered RbDDDs. And of course, on top of this basic idea, a lot of very nice optimizations have been done by these various papers. In particular, this paper by Fried and Tabahara recently did very nice optimizations to come up with a synthesis tool starting from input first ordered RbDDDs, which can even be given as in a factored form. It doesn't have to be given as one monolithic RbDDD. So very nice work. However, the point that I want to mention here, and maybe we'll take a break after that, is that for RbDDDs, we indeed know that the same function for some variable order can require an exponentially large RbDDD, and for another variable order can require a much smaller RbDDD. And in particular, if we're talking about relational specifications, this is a very simple relational specification saying that, if you think about it, the scaling functions for these are already given here in the specification, right? But if you try to represent this specification as an input first RbDDD, what you'll see is that you have to first represent all combinations of the inputs. And so you'll have to basically have as many leaves or as many intermediate nodes after you have read all the inputs as there are combinations of inputs. So there'll be 2 raised to n nodes at this intermediate level. And only after that, because you can't merge any 2 of these, because for every possible combination of inputs, there's a different combination of the outputs that's going to satisfy the specification. So you have to separate out all of them. And so at this intermediate level, you'll have 2 raised to n nodes if there are n inputs and n outputs over here. And so the size is omega 2 raised to n with input first ordering. But on the other hand, if you chose an ordering where you first had x1 and then you had y1, right? So you can say, okay, x1 can be either 0 or 1, and after that y1 can be either 0 or 1. And if the value of x1 matches the value of y1, then you go on to check x2 and y2, otherwise you directly come to the 0 leaf. So you can actually get a linear sized RbDDD if you were to interleave the inputs and outputs. But if you insist that you must have an input first ordering, then you get an exponential sized RbDDD. So this really shows, while this technique is very elegant and it really works very nicely when you get small RbDDDs with input first ordering, but you can really end up in bad corners over here. So I think I will. So Jakob, is this a good point to take a break, or should I continue?
No, I think this might be a good point. I actually have a naive question. So I didn't get, was it important in this example? So I'm probably revealing that I didn't get anything, but never mind. In this example that you're doing, is it important that you have this order y, that y2 is the first y variable and then y1 afterwards? Like it would have crashed if you had y1 first and then y2?
No. So you could have had, you could have any ordering on the output variables, but then the order in which you will be quantifying the variables and doing the compositions will be as per that order.
Yeah, that's what I mean. But can you could you say just a sentence or two, explain why this is so? Or
oh, okay. So as you can see, I guess the basic idea is that you want to separate the inputs from the outputs, and you want to sort of read all the inputs and then come to a point where the only decisions you're taking are on the outputs, right? And if let's say you are at this point. So let me understand your question. So you're saying that if I had a different ordering of variables, I could also very easily find out the scaling functions at these intermediate points. Is that what you're asking?
I'm trying to understand why this is not. I'm still sort of struggling to wrap my head around what's going on. So it's an attempt to understand, like, you know, if I would understand better if I understood why you couldn't do y1 first and then y2.
Oh, we could do y1 first and then y2. Absolutely. It would be perfectly fine.
No, but without switching the order. Like I
see.
Maybe I'm not phrasing the question well. That's fine.
Oh, I see. So you want to keep the same order in the RbDDD, but you want to first get y1 and then you want to get y2.
Yeah,
can I offer a suggestion? Can I offer a suggestion that might explain this? Jakub, I think he's saying that when the inputs come before the outputs, these are the x's, that's obvious. Now, in synthesizing the outputs, the order has to be such that the first output you put becomes an input to the second one, and the second one becomes to the third one. And so the outputs start behaving like inputs for the remaining outputs. So that's why the order will, whatever order you choose, you're going to get different column functions, but whatever order you use will make the second and third and fourth outputs dependent on the area outputs.
Thanks, Karim. That's extremely helpful.
Okay. Yeah, I think you explained it much better than I did. Thanks.
No, because I know BDDs. That's why. That's all.
Yeah, exactly. So I should have already taken the value of y2 and then proceeded. Yeah, Jacob. So should we take a break? I can take some questions and then take a break.
Let's see. Are there any more questions by voice or chat, or and then let's take a couple of questions if people have questions, and then we'll take a break.
Okay, sounds good. Yeah.
That requires us to ask some questions, though. So the people attending the talk will have to collaborate and ask some questions. Otherwise, we'll take a break right away. Let's see if we have any questions at this point. I don't see anything in the chat. I don't see anything in the Q&A. So I guess that means we're having a break, I think.
Yeah, I hope it doesn't mean that all I said was unintelligible, but yeah, I'm happy to take questions at any point. Yeah.
No, Supratik, it was very clear, actually. Just to let you know. Thank you.
Thank you.
So then let's reconvene at 13 minutes to the hour. So we're having a 10-minute break now, and then 13 minutes to the hour we'll be back. And if you want to
10 minutes.
Asking questions in the chat while we're having the break is perfectly fine. Okay, see you in 10 minutes.
Yeah, perfectly fine. Okay. Thank you.
Here's a matching video.
Let's see. Are we back? Maybe.
Hi, Jacob. Yeah, let me just turn on the source of noise from the background. Let me turn it off.
So everybody has had a chance to stock up on caffeine or whatever you need, depending on the time of day. I don't see any questions in the
Okay, Jacob. Yeah, I'm ready.
Good. We don't see your slides.
Is it visible?
It looks fantastic.
Okay. So let me know when I should get going.
So yeah, so I realized I have one question more. In this example that you did, that we have now, when you're looking at I look at y2. So
yeah.
So I guess x1 and x2, they're like given to me. I guess we read those as inputs and then we just walk accordingly. And then I've reached y2, and y2 is what I'm going to set. And for so I need to set y2 so that there exists choices of y1 that will take me to the one node.
Exactly.
Okay.
Exactly.
So if I may, a question about the ordering of the Ys. Are there some orders for which it becomes infeasible?
It becomes infeasible.
Like,
no.
Once you've chosen a particular value for y2, then there is no value for y1 that will take you to the one.
Oh, yeah. I mean, for example, in this case, if you choose y2 to be 0.
No. I mean, ever. I mean, so it makes it impossible. And ordering on the Ys, there are some orderings on the Ys that will make it impossible.
No, for every ordering of the Ys, we will be able to. So, an RbDDD has this property that once you're at a particular node, if there is no way that you can satisfy the specification, then that node will directly on the corresponding branch will directly lead to 0. Right? So if the node is leading to anything other than 0, you know that there is a path to 1. Right? And so because we are representing the same overall specification, regardless of the order in which we are putting the output variables. So for every ordering of the output variables, this method will, essentially, it's like saying that after I have taken a particular path through the inputs, can I reorder the BDD that's rooted at that point? Can I reorder the variables in the BDD rooted at that point, right?
And any ordering will always have a path to 1, is what you're saying.
Yes, because we are representing just the cofactor of the original specification with respect to the assignment on the inputs.
And so the different orderings of the Ys just give you different implementations of them, right? Different functions.
Yes, you could get different functions, but they will all be legitimate scoring functions.
Okay.
Yeah, they could be different scoring functions. Yeah.
Okay, thanks.
There should be also somewhere, I guess. So after the first elimination step, so like the RbDDD that computes y2 for us, am I right that it will read x1, it will read x2,
and it will have a one leaf
y1,
over here.
and then it will output like what value we wanted for y2?
No. So the RbDDD for y2 would be, it would read x1, read x2. So the RbDDD for y2 will look like the following. So at this leaf, it will have 1. Because when x1 is 1, x2 is true, y2 should be 1. At this leaf, it can be either 1 or 0.
I just pick arbitrarily. Okay. I see. Okay.
And at this leaf, it has to be 0. So if you sort of cut this RbDDD here and substitute a 1 leaf, and here it can go either to 1 or 0. So basically these decisions don't matter. And here if you put a 0 leaf, the resulting BDD would be right. So you could put a 0 here, for example, or if you could put a 1 here. Doesn't matter.
And then when I want to do y1, I will sort of take the RbDDD we had before and sort of contract away the y2 layer.
Exactly. So suppose you had chosen y2 to be 1 here. So now to get the RbDDD for y1, you will sort of, take the 1 branch from here, and let us say you had chosen the 0 branch here and the 0 branch there. So now your RbDDD looks like x1, x2 coming to this node, and this guy coming here. And so essentially this is, essentially these edges are sort of struck off. Edges corresponding to the values of y2 that you did not choose are struck off. And then you repeat the same thing for y1.
Okay, great. Thank you so much. Okay, so I guess we should let you continue.
Okay. So, Jacob, how much time do I have?
Well, I have been delaying you, right? So, how much do you need?
Just asking. Yeah, so I think if I have around 40 minutes, I think that should be fine.
Okay, yes.
Okay.
Let's go for it.
Thank you. All right. So this was about RbDDDs, and if you can represent it using the input first ordering, you're in business. But can we go beyond input first ordered RbDDDs? I mean, truly RbDDDs have much more structure than we need. And what if we're fine with Skolem functions as circuits and not as RbDDDs? Can we avoid the exponential blowups? What if the best variable order for the specification is not input first? We just saw an example like that. Can we do efficient synthesis for such specifications? And fortunately, the answer to that is a yes. And the next representation that we're going to look at is decomposable negation normal form, which was introduced by Adnan in a seminal paper. And there is a weaker version of that we also found works for the purpose of synthesis. But let me just talk about what decomposable negation normal form is, just summarizing, this special form. So here we have, phi of xy represented as a circuit, and this circuit is a negation normal form, which means all the negations are at the leaves. And if it is the case that for every AND gate in this circuit, you can't find 2 paths coming from 2 leaves that are labeled by the same variable, either with the same polarity or with opposite polarity. So it could be Z and Z over here coming here to meet in this AND gate. This is not allowed. And similarly, Z negation Z here, that is also not allowed. So if your circuit is such that the variables that eventually feed into one input of an AND gate, and this should be true for every AND gate. So if your circuit is such that for every AND gate, the variables feeding into one of its inputs are completely disjoint from the variables feeding into the other input, then this circuit is said to be in decomposable negation normal form. Of course, this generalizes to multi-input AND gate. It can be more than 2 input AND gates also, right? So the variables, not just the literals, the variables that feed into one gate of an AND gate must be completely disjoint with the variables feeding into another input of the AND gate, and this should be true for every AND gate in the circuit. So if your circuit has this property, then it is said to be in decomposable negation normal form, and DNNF has a lot of beautiful properties which Adnan talked about a week or so back. And what we are really going to use here is this notion called DNNF except on X, which is that we require this property that variables feeding into one input are disjoint from the variables feeding to the other input only with respect to the output variables. We do not care about the input variables. So we can show that if the specification can be represented by a DNNF circuit, by a circuit which is DNNF except on X, which means that no variables in Y feed, there is no single variable in Y which feeds both inputs of an AND gate, then the representation of the specification in this DNNF except on X allows you to synthesize Skolem functions in polynomial time and space. Okay, so let me repeat what I just said. So if your specification phi of xy can be represented as a circuit which satisfies this property, which is DNNF except on X, which means that for every AND gate in the circuit, the set of output variables feeding one of the inputs of the AND gate is completely disjoint from the set of output variables feeding another input of the same AND gate. And if this is true for every AND gate in the circuit, then starting from the specification represented by such a circuit, we can do synthesis in polynomial time and space. Okay. Now, this can be generalized slightly further, where we say that, well, DNNF would not allow two paths starting from, let's say, Z and Z over here to meet up at an AND gate. But we say that, well, it's sufficient if you just disallow paths coming from a variable and its negation. So in particular, it is okay to have a variable and the same variable feeding an AND gate as long as they're not in negated polarities. But you're not allowed to have a path going from a variable and its negation meeting up at an AND gate. So there's a slight weakening of the requirement that we have for a DNNF, and we call this weak DNNF. And once again, if your specification can be represented by a circuit which satisfies this weak DNNF property, then synthesis is once again doable in polynomial time and space.
And here we're using that in this for negations is only at like leaf level, is that right?
Yes, so these are a negation normal form circuits.
So that's why,
so
like if you have two Ys, then it's not like one of them will be flipped later on during the path. That's like how it works, because actually both of them are feeding in Ys all the way, right?
Mm-hmm. Exactly. Okay, and given any Boolean circuit, it can be converted to NNF, with at most a linear blow up in size. So converting a circuit to NNF is not a big deal. If you had negations inside, you just push them down, converting ANDs to ORs, ORs to ANDs, basically De Morgan's law. So that results in at most doubling the size of the circuit. So this is a very practical normal form in that sense. Okay, but of course, an NNF circuit may not be in DNNF or weak DNNF, and it's only when the circuit has one of these properties that we can say that synthesis can be done efficiently. Okay, so what we want to do now is, and the other nice property about DNNF and WDNNF circuits is that the quantification of Yi's and the composition of Fj's can be done in arbitrary order. Remember, we had fixed an ordering among the outputs, and then we were doing the quantification and composition in that order. But if you have your specification represented as a DNNF or WDNNF circuit, then for any ordering you choose among the outputs, you can go ahead and do the quantification and composition, and still you will get polynomial time and space synthesis. Okay. Now, so the the real contribution of our work is to ask that, is there a weaker than the weak DNNF representation that guarantees polytime synthesis? And the answer is synthesis negation normal form, which subsumes and is exponentially more succinct than the other forms. And then we ask that, can we synthesize Colem functions given a specification? Sometimes it becomes difficult to convert it directly to a syn and NF. So is it possible to simplify it in a very principled way and then convert it to our syn and NF? And so this is what we call refinement with respect to synthesis, and I'm going to talk about this as well. And finally, can we algorithmically compile phi to a refined syn and NF specification phi tilde? And we've done this implementation. The practical results look promising, but of course we must remember that there are complexity theoretic lower bounds. So this compilation does take super polynomial time in the worst case. In fact, currently it takes, in the worst case, exponential time. Okay, but there are a lot of other circuits that can be compiled to syn and NF much faster than exponential. Okay, so the classical notion of knowledge compilation is that it's a family of approaches for addressing the interactability of a number of typically artificial intelligence problems. And so a propositional model is translated or transformed in an offline phase to support several interesting queries which can be answered efficiently. So this is the typical knowledge compilation pipeline, that you're given a formula which maybe is a circuit or as a CNF formula, and then you compile it to a certain special form, could be a binary decision diagram, DNNF, what have you. But once you have this, then in polynomial time, you can answer several interesting questions that you wanted to answer about the original formula. So this is the typical view of knowledge compilation. So our definition of knowledge compilation for synthesis is pretty much the same, except that we are addressing the interactability of synthesis as opposed to those other problems like model counting, model enumeration, and all of that. So we take the specification phi as a CNF or as a circuit. And of course, we must know what are the inputs and what are the outputs in the specification. We saw in the factorization example, it makes a big difference if you flip the roles of inputs and outputs. And then we want to get this new specification called refined syn NNF. The reason we add this refined and not just the syn NNF is because we find that by doing this refinement, we can actually get much smaller representations while still guaranteeing that whatever Colem functions we synthesize out of this refined syn NNF are also Colem functions of the original specification. So in our knowledge compilation pipeline, this phi hat may not be semantically equivalent to phi, but it satisfies a refinement relation with respect to phi. But what it does guarantee is that because it's in syn NNF, we can now synthesize Colem functions from it, and every Colem function synthesized from this refined syn NNF is also a Colem function of the original specification. Okay, so the way we proceed is by starting off with the same NNF DAG that we saw for DNNF and weak DNNF. And here is a particular example. This is an NNF DAG where I have kind of shown the leaves separately, but in reality, these would probably be merged together to have a DAG. And, these are the leaves that have negated outputs on them. And what we want to do is we want to replace all leaves which have negated outputs on them with a fresh variable. So in this particular case, negation negation y1, I'll replace it with y1 bar, and negation y2 with y2 bar, where y1 bar and y2 bar are fresh variables. They are not the logical negations of y1 or y2. And because I have done this change in variables here, so at the root, the function that is being represented is no longer the original specification. It's a new specification, phi hat, which is of course related to the original specification. And we call this new specification phi hat the positive form of the specification. So it has all the leaves which had inputs on them unchanged, and all leaves which had the outputs in positive form unchanged, and all leaves which had outputs in negative form are replaced by these new bar variables. And that's the new circuit we have. And because this is an NNF circuit, which means all internal gates are just AND and OR gates, it's now easy to see that this circuit is monotone with respect to the outputs and the bar of the outputs. Okay, there are no negations that you're going to encounter if you start from an output or a bar of an output and go all the way up to the root. The only negations remaining on the leaves are for the inputs. Okay, so there are some simple properties of this phi hat circuit, and here is one. So if I take phi hat, remember from phi, I constructed phi hat by relabeling the leaves that had negations of outputs as their labels. So if I take the circuit phi hat and substitute for every leaf which has either y1 or y1 bar, if I put the constant 0 there, now remember, if this y1 bar was a negation y1, I couldn't have done it, because if y1 was 0, negation y1 would have to be 1. But now, because I have a new variable here, I can do it. And that's exactly what I want to do. So if I replace y1 and y1 bar both with 0, then I get an under approximation of there exists y1 phi. And if I replace both of them with 1, then I get an over approximation of there exists y1 phi. And this is not very hard to see. Okay. Of course, you know, when I say under approximation of y1 phi, the other variables, which is like negation y2, stays as negation y2. It is, so essentially y2 bar is converted back to negation y2. It's just the y1 and y1 bar, the variable that you're quantifying, that variable and its negation, they are, I mean, not the negation, the variable replacing the negation leaf, they're both set to 0. Okay. Now I could do this for two variables also. Like if I want to quantify two variables, then once again, all the variables I'm quantifying, I will change the negation leaves, the negations of them appearing in the leaves to the bar variables. And then I'll set all of them to 0 to get an under approximation of exists y1 by 2 phi. And I'll set all of them to 1 to get an over approximation of y1 by 2 phi. And this turns out to be a very simple way, a very easy way to get an under approximation and over approximation of quantifying out a bunch of output variables from the specification. Recall that we needed to quantify out a bunch of output variables when we were talking about how to reduce synthesis for multiple outputs to synthesis for a single output. So this is kind of what we have. I mean, this is you know, formalizing what is given in the diagrams, that if I look at the outputs, so let's say there is y1 to ym as the outputs. So I'll have y1 bar to ym bar as the corresponding bar variables here. Now, if I set the outputs y1 to yi as 0, and the corresponding barred variables over here as 0, and the other variables, I make them the negation of the corresponding variables over here, then this gives me the under approximation of quantifying out these yi variables from phi. And similarly, if I do this for 1, basically replace these with 1, but the other bar variables, I set them back to the negations of the original yi variables, then I get an over approximation of this quantification. So this is not very hard to show. This just follows from the monotonicity of the circuits with respect to yi's and yi bars. But now this has a very interesting consequence. And
so
this
just
is kind of
question.
Yeah.
So we're doing this on a base NNF, right? No properties. Just these substitutions are being done on a base. We're not require any additional properties. Okay, thank you.
No additional properties. Just a base NNF. We know which are the outputs and which are the inputs, and we're just going and relabeling negation outputs on the leaves. That's all. No other property.
All right, thank you.
Okay. Yeah. So okay. So now this sort of leads to, you know, kind of the central idea that gives us the synthesis negation normal form. So what we do is we, given a specification, we convert it into its positive form, which is basically replacing all negated output leaves by fresh variables. We use a linear ordering of the outputs, and then we define this quantity which we call the ith reduct of phi hat, which is obtained by just setting y1 to yi minus 1 to 1 and y1 bar to yi minus 1 bar to 1, retaining yi as is and yi bar as is, and setting all the other yi plus 1 to ym bars to the negations. So, we're basically saying that this is the ith reduct, so the ith variable is special. So we are going to keep yi and yi bar unchanged. Whatever comes before yi in the ordering, we're going to set them to 1 both in the normal variable and the bar variable form. Whatever comes after yi, we're going to set them to the normal variable and the negation of them. Okay, so this is what we define as the ith reduct of phi hat. And here's a simple example. So for example, the first reduct is just replacing, there are no variables before the first variable to set to 1. So we just keep y1 bar, and the other variables y2 and so on, we just keep them as is, and their barred variables we just put negation. Okay, so phi hat 1 is kind of just setting all the variables other than y1 and y1 bar to their usual forms, which is yi and negation yi. But phi 2 hat is interesting. Phi 2 hat is obtained by setting y1 and y1 bar both to 1, because now if I is 2, then I have to set all variables before and the barred of those variables before to 1. And whatever output variables come after that, I'll set them to their negations in the bar form. Here, there are no variables after y2, so nothing to set to their negation form in the bar. But y2 and y2 bar stay as they are. So here there is only y2 bar. So you notice that phi hat, the second reduct of phi hat is not exactly the same thing as just, setting. It's not exactly the same as quantifying out y1 and keeping y2 and y2 hat, right? Because we are replacing y1 and negation y1 with y1 bar and then setting both of them to 1. If I were to quantify out y1, I would have to set this to 1 and 0 or to 0 and 1, but here I'm setting both of them to 1. And because we need this ability to set both of them to 1, that is why we did this renaming of variables, right? So the second reduct of phi hat is obtained by setting both y1 and y1 bar to 1. If there were variables after y2, we would keep them in the normal forms and the usual forms. That is, the usual variables will be as they are, and the barred variables will be the negation. And the special variable with respect to which we are doing this reduction stays in the normal form and the barred form, right? So here it is y2 bar. So, these are just examples of what phi hat, the first and second reducts of phi hat would look like. And we can now do this for, all i's. And why do we want to do this? So I think this slide is going to be the central slide, which explains why we want to do this. So we've already seen that if I were to quantify out a particular variable, then I can over approximate that by taking phi hat and setting y1 and y1 bar to 1 and renaming all the other bar variables by the negations of the corresponding variables. So this is the same as taking the first reduct and setting y1 and y1 bar to 1. Because in the first reduct, there are no variables before the first variable, so there is nothing is set to constants. And because I'm setting y1 and y1 bar to 1 here, so I'll just set those to 1. So we've already seen that the result of quantifying out y1 from a specification can be obtained by setting y1 and y1 bar to 1 in the first reduct. Now we want to ask, under what conditions am I going to get the implication in the other way? Okay, so specifically, we want to know that when does the implication in the other way get violated? And then if we can avoid those situations, then I can actually obtain the result of quantifying out y1 from the specification by just taking the first reduct and substituting y1 and y1 bar to 1. So we want to find out when does the implication not hold in the other direction, right? What does it mean? That I want phi hat 1 with y1 set to 1 and y1 bar set to 1 to evaluate to true, but I want exists y1 phi xy to evaluate to false. But what is exists y1 phi xy? It is exactly phi with y1 set to 1, disjuncted with phi with y1 set to 0. And we know that phi with y1 set to 1 would be the same as phi hat with y1 set to 1 and y1 bar set to 0. Right? If you set y1 bar to the negation of y1, then it's pretty much that we have not done any change. So it is just setting phi with y1 to 1. And similarly, phi with y1 to 0 is phi hat 1 with y1 set to 0 and y1 bar set to 1. So this is the interesting part, that when I choose to set values to y1 and y1 bar, which are just the complements, the negations of each other, then it is as if I'm setting the variables in the original specification to specific constants. But then because I have renamed negation y1 to y1 bar, I also have this ability to set both of them to the same value. Okay. And I know that that already over approximates the existentially quantified formula. So when does this implication not work in the other direction? Exactly when phi hat 1 with y1 and y1 bar both set to 1 is 1. But when you set these to 1, 0 and 0, 1, they're both 0. And by monotonicity of phi hat, if both of them are 0, then when I set both y1 and y1 bar to 0, then I must also have 0. Remember, this is monotone with respect to y1 and y1 bar. So, if I reduce one of the inputs, the output cannot change back from 0 to 1. Okay, but now if you look at it, if I look at the function phi hat 1 as a function of y1 and y1 bar, so when both of them are 1, I want it to evaluate to 1. And when any one of them is 0, I want it to evaluate to 0. So this is exactly saying that we want phi hat 1 to behave like y1 and y1 bar. So this implication in the other direction fails when phi 1 hat behaves like the conjunction of y1 and y1 bar. Okay, so if we can stop phi hat 1 from behaving like the conjunction of y1 and y1 bar, then this implication will not fail in this direction, and we will get an equivalence over here. Right? The result of existentially quantifying out y1 would be the same as phi hat 1 with both y1 and y1 bar set to true. So the insight that we have is that the result of quantifying out y1 from phi would be logically equivalent to phi hat 1 with both y1 and y1 bar set to true for all x and y2 to ym if there are no values of x and y2 to ym for which this behaves like y1 and y1 bar. Okay, so I cannot find any value for x and y2 to ym such that this behaves like y1 and y1 bar. When I substitute those values, if I can ensure this, then these two will be logically equivalent. And I can now inductively extend this argument by saying that I can get the result of quantifying out I variables by taking the ith reduct and setting y1 and y1 bar to 1, right? If I can make the ith reduct not behave, so the ith reduct should not behave like yy and yi bar for any values of x and the other remaining variables. So all that this is saying is that if you can reorganize your circuit or restructure your circuit such that you have this property that phi hat 1 is never going to behave like y1 and y1 bar. Phi hat I is never going to behave like yi and yi bar. And here you can see where the definition of the weak DNNF comes in. If there is no path to an AND gate which can come from a variable and the negation of the variable, then this phi hat 1, this iterated reduct can never behave like this AND gate, right? And so this is the crucial idea that we want to say, that an NNF specification is in synthesis negation normal form with respect to a linear order if for every I in 1 to n, I have this property that the ith reduct does not behave like an AND gate, right? Which means that, if you look at this formula can be, because there's just yi and yi bar, two variables here, I can expand it out into sort of 4 combinations. So I can say that phi hat I with yi set to true and yi bar set to true, either that should not evaluate to true, or phi hat I with yi set to true and yi bar set to false, that should not evaluate to 0, or all the 4 combinations. So this basically becomes a disjunction of 4 formulas involving phi I hat when we want this equality not to hold. with this equivalence not to hold. And we just want to check that formula is not satisfiable for any values of the input variables and the other remaining output variables. Remember, phi hat I already has the variables y1 till yi minus 1 already replaced by the constants 1. So the only other variables are yi bar, and yi plus 1 to ym. So, informally, we are saying that can phi hat I be made to behave like this for any I? And if the answer is yes, then it is not in SYN-NF. Otherwise, it is in SYN-NF. And once we have phi in SYN-NF, then the Skolem function for yi can just be obtained by, we have already seen this, that we can existentially quantify out the prior variables and set the variable to 1. So this can be obtained by as just taking the ith reduct and setting yi and yi bar to 1 and 0. The ith reduct effectively quantifies out the previous variables, and then you just set yi and yi bar to 0, yi to 1 and yi bar to 0 to mimic setting of yi to 1. Okay. So, so this looks like that if we can have this complicated condition on the representation, then we can ensure that synthesis can be done in polynomial time and space. Now this condition looks complicated because we are essentially talking about not a syntactic or a structural property, but a semantic property. Right? We're saying that give me a circuit and then give me an ordering of the outputs, and then I want to check if I set y1 till yi minus 1 to true and y1 bar till yi minus 1 bar to true, then can I make it behave like yi and yi bar? Okay, so this is just a SAT check, and we can do this by just doing the SAT check for a given order. So the restriction is not purely structural, it's not purely syntactic, it is a semantic restriction, and this is actually reminiscent of another very popular normal form that is there in the literature due to Adnan and his students, which is called deterministic decomposable negation normal form, where you have decomposable negation normal form at every AND node, that condition for every AND node, and for every OR node, you require that the two subformulas feeding into that OR node should be inconsistent, should be mutually inconsistent. So this is a semantic form which is already there in existing normal forms in the literature, and SYN-NF is also in that same spirit. It's just that this condition is slightly harder to state, but algorithmically it is not very hard to implement this check, because we just take an ordering and we just keep checking whether this equivalence holds, and this is just a SAT check. Okay, so now let me just give a few examples. So here is a formula phi written as an NNF tree, and if you notice that this formula is not in decomposable negation normal form because you have y2 and negation y2 going and meeting up at an AND gate. It is neither in weak decomposable negation normal form because you have y2 and negation y2 meeting at the AND gate. However, we're going to show that this is in SYN-NF, synthesis negation normal form, for this output sequence, y1 before y2. So why is it in SYN-NF with respect to this output sequence? So we first ask that, well, can I make this circuit behave like y1 and y1 bar for any values of the other variables? Now notice that there is no negation y1 here, so there is no y1 bar. So obviously this circuit cannot be made to behave like y1 and y1 bar. Okay, so all good. Then we say that, okay, now let's look at y2, but when looking at y2, I'm going to set y1 and y1 bar both to true. There is no y1 bar here, so I'll just set y1 to true. And then I'm going to ask in the resulting circuit, can I make it behave like y2 and y2 bar? Now, because I had set y1 to true over here, therefore this y2 no longer has a way of reaching this AND gate. It's effectively masked. And therefore this circuit can no longer be made to behave like y2 and y2 bar. And therefore this satisfies the SYN-NF requirement for y2 as well. So for this sequence, y1 before y2, this representation is indeed in SYN-NF. Now what happens if I flip this? If I say that, would it be in SYN-NF with respect to y2 and y1? So in order to do that, I have to ask, well, can I make the circuit behave like y2 and y2 bar? I have replace the negation y to leave with y for some valuation of the other variables. Now here, if I indeed set y1 is 0 and x1 is 0, then I can, and I believe x2 to 1. So then I can indeed make this like y2 and y2 bar at the root. And this means that this circuit is no longer in SYNNF with respect to this sequence. Okay. So the same circuit can be in SYNNF with respect to one sequence of outputs and not with respect to SYNNF with respect to another sequence of outputs. So of course, checking whether it is in SYNNF with respect to some sequence of outputs is a hard problem. Turns out that's in sigma 2p. But given an output sequence, we can easily check it by just doing these SAT checks. Okay. Now, what is the relation between BDDs and SYNNF? So here is another BDD. I'm not sure if the dotted edges are very much visible here. So, I can convert each node in a BDD. Remember, this was representing that if y1 is 0, go down this path. If y1 is 1, go down this path. So I can replace this node by a circuit where I have an OR gate here. And on the left, I have negation y1 conjuncted with whatever is the circuit corresponding to the BDD hanging here. At the left as the left child, and on the right side I have y1 conjuncted with whatever is the circuit corresponding to the BDD hanging here as the right child. So I can recursively do this transformation for every node, and as you can see, this just gives a linear blow up, and this allows me to convert any BDD, reduced order BDD, into a circuit like this. And in this circuit, if you notice that every variable, every output variable and its negation, in fact, every variable and its negation will never meet up at an AND gate, because the first time they meet up is at an OR gate. Okay, there's no way that they want to meet up at an AND gate coming from two distinct paths. So this already satisfies the SYNNF property. And of course, this is true even for DNNF. I mean, this transformation also converts RbDDD to a decomposable negation normal form. What about decomposable negation normal form and weak decomposable negation normal form? If you remember the property that you can't have the same variable coming and meeting at an AND gate through two of its inputs, this automatically precludes having something like yi and yi bar, because at an AND gate you can't have the same variable coming from two different inputs. And similarly for weak DNNF, because we specifically exclude things like yi and negation yi. So when you replace this negation yi by yi bar, you cannot have an AND gate which satisfies, sort of implements yi and yi bar. So that's also ruled out. So a specification in DNNF or WDNNF is already in SYNNF, and this is for any output ordering. And here are some interesting observations about SYNNF, that every propositional formula is, of course, representable in SYNNF for every ordering of outputs. For example, disjunctive normal form is always in SYNNF for any output order. A formula may have multiple SYNNF representations. We have already seen these, RbDDDs, DNNFs. Indeed, a given representation may be in SYNNF for one order of outputs and not in SYNNF for another order of outputs. And given an output order and an NNF specification, to check if that is in SYNNF requires these SAT calls, really unsat calls. We want to show that the iterated reduct is not equal to the conjunction of yi and yi bar. So it's going to be complete. But if you want to, given a circuit, an NF circuit, if you want to check if it is in SYNNF with respect to some unspecified order, then that turns out to be in sigma 2p. And indeed, we have been able to show some succinctness results as well, which means that there do exist polynomial sized SYNNF representations that only admit exponential sized RbDDD or functional decision diagram representations for any ordering of the input variables. The same is true even for DNNF. So there exist polynomial sized SYNNF representations that admit only exponential sized DNNF representations. There are we do not yet have a result about exponential sized deterministic DNNF, but we do have this conditional result that it will lead to super polynomial size deterministic DNNF unless P is equal to V and P. So these are two complexity classes which are not known whether they are equal or not. But at the same time, SynNNF is not necessarily the most succinct way of representing a specification. We do know that there are polysized NNF representations that only admit super polynomial sized SynNNF representations, unless the polynomial hierarchy collapses, of course. And so here is some kind of an ordering. So NNF is exponentially more succinct than SynNNF, which is exponentially more succinct than DNNF. I believe this is also exponentially more succinct than DDNNF. Not exactly sure over here. I don't recall. Adnan is, of course, the authority.
Yes, it is Supratik.
Yeah, thank you. And of course, deterministic DNNFs are exponentially more succinct than RbDDDs. So, so that's like locating where SynNNF is in this entire knowledge compilation map, as Adnan had proposed. And what about how easy is it to sort of take conjunction, disjunction with SynNNF formulas? So if I give you two formulas in SynNNF and both are
just
question.
Curious.
Yeah, sure.
So for interrupt, but just like the previous slide, getting these containments unconditionally. Do you think like because you need like without any assumptions about the polynomial hierarchy, or do you think this will be hard? And,
Yeah,
like
so,
V and V and P and stuff.
Correct. So there are two containments which are conditional, which is this NNF to SynNNF. Currently, it is conditional, but I believe this, we have been thinking about to make this unconditional. But currently, this is conditional. This exponential gap. This is not conditional. SynNNF to DNNF is not conditional. DNNF to DDNNF is also not conditional. I mean, we know that SynNNF to DDNNF is super polynomial unless V is equal to NP. So, I mean, it is the case that the circuits that show this gap may not be the circuits that show a doubly exponential gap over here, right? So each of these gaps are shown by a specific class of circuits, and they are not necessarily always compatible. And of course, this is also unconditional. So I guess in the containment relation shown here, this one is conditional, and SynNNF to DDNNF, we have only super polynomial sized, which is conditional. But if you look at them pairwise, then it's only this one which is conditional right now.
Okay, thanks.
So I had a question about when you are constructing SynNNF, then earlier you mentioned that it should not behave like the AND gate, but then you said that it can be just checked with the set call, because the formula is still defined in terms of rest of the variable.
Yeah, so we want to check with the SAT call that it doesn't behave like an AND gate. So it's a co-NP call, right?
Okay.
Yeah, so I mean, just to, I guess this picture showed it here, that we want to check whether Y2 and Y2 bar, is there any assignment of values to the other variables after you have set Y1 and Y1 bar to 1, which will make the output behave like Y2 and Y2 bar. And if that satisfiability call says yes, there is an assignment, then this is not in SynNNF. If it says no, then it is in SynNNF. I mean, you have to repeat this for all the variables in order, so it is in SynNNF then. Okay?
But then for most of the cases you covered, you actually won't need this SAT call because you have like a structural argument why it will pan out.
Yes. So the structural argument is weaker than what, as I showed that this circuit was not in DNNF or WDNNF, but it turns out to be in SynNNF. So there are circuits which are in SynNNF which may not satisfy the structural properties, but of course the structural properties are easier to check. They're far easier to check, right? Okay. So yeah, let me quickly try to wrap up. Yeah. So what about the operations? So it turns out that computing the conjunction of two formulas given in SYN and NF, both with respect to the same ordering, unless P is equal to NP, we can show that there cannot exist such a polytime algorithm. However, computing the disjunction can be done in constant time. You just put an OR gate and connect them up. That does it. You want to existentially quantify out the entire set of output variables with respect to which you have shown that these are in SYN and NF. That takes linear time. We have seen we just need to set the corresponding leaves and the bar of the leaves to 1. However, if we want to quantify out some arbitrary subset of y, this is not possible in linear time in general, although DNNF and WDNNF will allow you to do this, but not SYN and NF in its most general form. Okay, so how does SYN and NF help in scaling function synthesis? Just give me a second.
So I'll use the opportunity to highlight what is already there in the chat, that for people who wish to gather after the talk, there's Gather Town, and I put the link in the chat. Thank you, Antonina, for reminding me that there's a special workshop space, and you can all go there and meet each other. And it's like, almost like in real life. There are minor differences, but you won't notice probably. And sometimes even the speakers make it there, although I think it's getting close to midnight in Mumbai, so I don't know if it's fair to expect that. And people are still asking questions in Singapore closer to 2 a.m. So that's really being passionate.
Yes.
Anyway, so yes, our speaker is back.
So this is just showing that if you have your specification in SYN and NF, then basically you start quantifying out the variables and setting the remaining single output to 1 and 0, and you get a scaling function. Then you substitute that scaling function, quantify out the remaining variables, and so on. So if you start with your specification in SYN and NF, you can actually get all the scaling functions. You can get a circuit with all the scaling functions, which is m times the size of the original circuit, and with order m squared additional wires. And so this is what shows that, and this composition scheme and this setting of things to constants, this basically achieves the quantification, and this composition is of course composition. So this is what allows us to get a polynomial time and a polynomial sized solution to the Boolean functional synthesis problem. Okay, so as I promised, I'll just take maybe 2 more minutes to talk about this notion of refinement. And suppose I have a specification phi of xy, and let us say that this blue box represents values of x, and this blue oval within it represents all those values of x for which there exists some y, such that phi of xy can be satisfied. And this red box here are all the scaling functions. So this is the space of all scaling functions. And the things within this blue oval here are the scaling functions that suffice for this particular formula phi. Okay, so here is the space of all valuations of x, and for these valuations I have a y, such that phi of xy is true. And this is the space of all scaling functions, and this is the subset of scaling functions which I can use for y in the specification. So we say that a specification of phi tilde on the same input and output variables is a refinement of phi if it satisfies the following 2 properties. The set of x's on which there exist y's such that phi tilde is true is at least as large as the set of x's for which there exists y such that phi is true. But the set of scaling functions which suffice for phi tilde is a subset of the set of scaling functions that sufficed for phi, right? So you have more x's where the specification can be realized, but you have fewer scaling functions which can realize that specification. And if this is not a superset but an exact, it coincides exactly with the values of x for which there existed y, so that phi of xy is true. We call that a strongly refined spec. And then, we have this lemma which says that if phi tilde is a refinement with respect to phi, then every Skolem function vector for y in phi tilde also serves as a Skolem function vector for y in phi. And here's a simple example. On the here in the second line, I have a much bigger, more complicated specification in terms of x1, x2, y1, and y2. And it turns out that y2 and y1 is a refinement, satisfies exactly those two properties that we said relative to this, which means that every Skolem function that I can synthesize from y2 and y1, and this is very easy to synthesize, just set both of them to true, will also serve as a Skolem function for the original specification. So the notion of refinement with respect to synthesis allows us to simplify specifications without losing the ability of finding a solution. So it is something like the equisatisfiable reduction. But of course, here, as I said, the number of possible Skolem functions reduces, which means that the total space of solutions that I could have here could be less than the space of solutions that I have here. But sometimes that actually helps in synthesis. If you have fewer solutions, you need to search over. Okay, and then there are some nice properties of this refinement. Both of them are reflexive and transitive relations. And then, so I will skip over these in the interests of time. But essentially, there are several properties, compositional kind of properties that you have that, for example, I think this property is very interesting. So if F1 tilde is a strong refinement of F1 and F2 tilde is a strong refinement of F2, then F1 tilde disjunction F2 tilde is a strong refinement of F2 tilde. And if you want for the conjunction, then F1 tilde conjunction F2 tilde is a strong refinement of F1 conjunction F2 if there are some side conditions that have to hold. Right, some output supports of F1 and F2, and similarly of F1 tilde and F2 tilde have to be disjoint. Okay, so this actually allows us to look at a specification. Remember, our specification is a circuit. So we look at sub-circuits, convert them to refined specifications, and then we combine these refined specifications to get the overall specification as a refinement of the original overall specification. And this has all been put together in a tool called C2SYN, which takes input in CNF and it generates a refined SYN-NNF specification, which can, after that, of course, be used for synthesis. And this kind of uses the same techniques as are used for generating deterministic decomposable negation normal form. So, we look at the specification, choose a suitable ordering among output variables, branch on the output variables, and then for each subproblem, we try to come up with a refined specification that is in SYN-NNF rather than a semantically equivalent specification in SYN-NNF. And the details of this algorithm are there in our paper. So we did some experimental comparison with the QBF eval, the two QBF formulas in the QBF eval benchmark and the factorization benchmarks, total of 408. This synthesis thing actually has multiple stages. The first stage checks whether the given formula, with some very minimal manipulations is already in SYN-NNF. So we do that check whether it's behaving like an AND gate. And it turns out that a large number of them are already in SYN-NNF with some very minimal manipulations. And then, the rest of them, we have to, again, go and transform them to get them in SYN-NNF. If you look at BDD compilation, then of course, if you compile them into BDD, then of course they're already in SYN-NNF. So we can basically sort of, and this BDD can be compiled with respect to any variable order. It doesn't have to be output variable. It doesn't have to be input first, because BDDs are just a subclass of SYN-NNFs. And so here is kind of the final slide where I just want to point out these scatter plots, which show that we compared this with two other techniques. This is kind of the guess check repair paradigm, and this is the incremental determinization, which uses the things CDCL heuristics to do Boolean functional synthesis. And I guess the picture that comes out from these plots is that these are kind of incomparable techniques, and so perhaps they're best used in a portfolio mode. For some benchmarks, something works better, some others, something don't work better. But I must also say that the implementation of C2SYN that we have is a highly non-optimized implementation, whereas KDIT is a significantly optimized implementation. So there is further work that we're trying to do to optimize the implementation. So in conclusion, we talked about a new normal form for polynomial time synthesis. We talked about refinement, and CNF to refined SynNF is much more efficient than CNF to SynNF. And experimental results show promise. And in recent ongoing work, we have been able to show that even the SynNF requirement can be further weakened to achieve polytime synthesis, but that's still part of ongoing work. So I must thank all of you for staying back so late. If there are any questions here or in gather.town, I'll come over to gather.town. I'd be very happy to answer them.
Thanks a lot, Supratik, for a fantastic talk. So we have questions.
Just a question, Supratik. Is SAT easy on SynNF?
So if you want, yes. So if you say that all your variables are output variables, so I give you a formula, right? So I take a formula phi of x, and I want to check whether phi of x is satisfiable or not. So I treat all of the x's as output variables, and I construct a SynNF form with respect to all of x's. Then, because we can do quantification, very easily just by setting the leaves to 1 and the yi and yi bar, in this case xi and xi bar, to 1. So I can actually quantify out all of the variables. And so if I'm able to, so if you give me a formula, if I convert that formula to SynNF with respect to all of its variables, the entire support, then yes,
right. So you need, that's the point. So not for an arbitrary split of x and y.
No. All the variables have to be treated as y.
Okay, thank you. So this is interesting because the problems you care about, there is a split of x and y, and it turns out that you have a form that would not be easy for SAT, but would allow you to do synthesis, which is interesting. So,
pardon me. Yeah. So it's a form which doesn't allow you easy SAT if you don't convert all the variables to. I mean, if you want to,
but still allow you to do easy synthesis, which is interesting.
Absolutely. And I think this kind of dilemma is kind of best explained by that I can take the same specification and reverse the roles of inputs and outputs, and I can certainly turn an easy synthesis problem into a very hard synthesis problem, factorization being an example. So what is an input and what is an output makes a lot of difference.
Right, and I think it probably has to do with the fact that you do not require the synthesized function to have any particular form. You don't require it to be tractable. You just want it. You just want the function. And okay, thank you. Yeah,
that is true. That is true.
That's interesting.
If you wanted the synthesized Skolem functions to also be in SynNF with respect to x for whatever reason, or to be in DNNF or something, then it would be much harder.
Right.
So we are looking at I mean that would be an interesting line to sort of explore. But currently we are looking at applications where once you get the circuit which synthesizes the Skolem functions, you're happy.
Good. So do we have any other questions before those of us who can move over to GatherTown? So I don't see, so we will of course had lots of questions during the talk already. So then I think on behalf of all of the audience, let me thank you, Supratik, again for a wonderful talk. And yeah, thank you so much. And we'll meet again in a week or on GatherTown in a few minutes. Thank you so much.
Okay. So I'll be there on GatherTown if somebody wants to discuss something further. I'll be happy. Okay. So